So hi everyone, and welcome to today's class. Today we are looking at hypothesis testing, and as we mentioned earlier on, hypothesis testing is part of what we call inferential statistics. We have looked at confidence intervals and also point estimation. So in this class, we shall be looking at hypothesis testing. And as I've mentioned, an hypothesis is just a claim. So we can start by saying that an hypothesis is an informed, you can also say sometimes is an educated or intelligent guess. It is an informed guess or an intelligent guess or claim, or you can say statement, an informed claim or statement or guess regarding a particular descriptive measure of a given population. Now, what I'm calling a descriptive measure of a given population is what we call a parameter. So it's an informed guess about a certain parameter. Remember, as we mentioned in our previous classes, parameters are always unknown, okay? Parameters are always unknown, and that's why we only make some guesses, but very intelligent guesses about them, okay? Then we say that this claim is usually informed by the researcher's experience, or past research findings on the subject matter under investigation. So the claim that we are talking about here is not based on ignorance. You base it on your experience or some available information, either findings of some past research and so on and so forth. Okay. Then we say that in order to find out if a certain set of sample data, in order to find out if a certain set of sample data comes from a particular population, we choose one descriptive measure. Of that population. You can talk about, for instance, e.g., a measure like population mean, population proportion, population variance, etc., and then test to see if it is likely Just to see if it is likely that the sample belongs to that population. So the population we are talking about is the one that we have hypothesized about. So after you make the claim, after you define your hypothesis, it is good that you check whether that claim is consistent with available sample data. So you'll be computing the corresponding descriptive measure from that sample, and then you compare the sample value and the hypothetical value, that is the guessed value, and check whether they are actually consistent. Check whether they are actually consistent. Now, this is what we call hypothesis testing. So this is what we call, or this is called hypothesis testing. So that's what we call testing of hypothesis. So you make the claim, then you pick a sample, you compute the statistic or the corresponding statistic, and then you check whether that sample seems to come from the hypothesized population. Then let's move on by saying that there are two types of hypothesis. There are two types of hypothesis. Number one, we have what we call the null hypothesis. The null hypothesis, which is usually denoted by H naught. Usually denoted by H naught. And this hypothesis asserts that or claims that the sample belongs to the population. The sample belongs to the population. That's what we call the null hypothesis. The number two, we have what you call alternative hypothesis. This is denoted by H1. H1. And we say that this hypothesis claims that or asserts that the sample does not belong to the population. The sample does not belong to the population. Okay. Then we can note that hypothesis testing involves collecting evidence, and this evidence comes from samples, or let's say from a random sample, from samples, with an objective of rejecting the null hypothesis. With an objective of rejecting the null hypothesis. So in short, hypothesis testing revolves around the null hypothesis. Okay, so if we have enough evidence, to reject the null hypothesis, we say that the test is significant. Otherwise, it is insignificant. otherwise it is insignificant. Okay. Then we can continue by saying that since sample measures, things like what? Things like X bar, things like P, things like S, etc. Since sample measures are variables. That's what we said when we were introducing the concept of sampling distributions. If you remember, we looked at an example where we computed mean from all the possible samples of a given population, and we observed that there were different values of X bar, starting from 1.0, 1.5, 2.0, 2.5, and 3.0. So we observed that X bar can be looked at as a variable, So we're saying since sample measures are variables, comma, we say that when testing hypotheses, we run the risk of making wrong decisions, in two ways. We run the risk of making the wrong decisions in two ways. Okay. And just as I've mentioned up there, is that hypothesis testing revolves around the null hypothesis, H naught. And this being a claim or a guessed statement, then the fact of the matter is that it is either true or false. So H naught in reality is either true or false. But now we end up collecting evidence from samples to reject that statement, or we fail to reject that statement. So it's good to appreciate the fact that you can reject the null hypothesis when it is true. You can also reject the null hypothesis when it is false. You can also accept the null hypothesis when it is true. And you can also accept the null hypothesis when it is false. So there are 4 possible decisions that you can make. And we're saying 2 of them are incorrect decisions. So I'll use a diagram here to illustrate all the possible decisions. Then from there, we shall be able to identify the wrong and the correct decisions. So everything revolves around H naught. And then we are saying that this is either true or false. Any statement that you make, whether it is an hypothesis or not, any statement that you make is either true or false. Okay. But now, once we collect evidence from the samples, we may end up doing this. You can reject or you can accept. Even when you are here, you can reject, you can accept. Okay. It's good to note that whether the hypothesis is true or false is not known to the researcher. You don't know. You just make a guess based on your experience or your knowledge about the subject matter. So when you look at this, there are 4 possible decisions or 4 possible combinations. The first one, you reject a true null hypothesis. You reject a true null hypothesis. So is that a correct decision or a wrong decision? Yeah, so as we have observed, if you reject a true null hypothesis, this will be a wrong decision. If you accept a true null hypothesis, this will be a correct decision. If you reject a false null hypothesis, this will be a correct decision. And finally, if you accept a false null hypothesis, this will be a wrong decision. So we're saying that there are two ways when testing hypothesis, there are two ways in which you can make the wrong decision, this way and this way. So the first way of making the wrong decision here, this is called type 1 error. And this one is called type 2 error. Type 2 error. So I want us to proceed. So we're saying that when testing hypothesis, we run the risk of making the wrong decision in two ways. That is rejecting a true null hypothesis resulting to what is called type 1 error. Resulting to what is called type 1 error. Resulting to what is called type 1 error. Or failing to reject. And here you should, I need to say that you avoid using the word accept. Avoid using the word accept. We're saying that failing to reject a false null hypothesis resulting to what is called type 2 error. So when testing hypothesis, you run the risk of making type 1 error and type 2 error. Okay. Then we say that, for instance, before I say this, for instance, we can consider this illustration in the corridors of justice. When a suspect is arraigned before the court of law, the initial assumption is that the person is innocent until proved guilty. So that's the initial assumption of the judge or of the court, that every person or every suspect is innocent until proved guilty. So this is like a null hypothesis. So because we have this hypothesis, it is the work of the prosecution or the prosecutor to collect evidence with an objective of rejecting this statement. And that's what we said. The objective of hypothesis testing is to collect evidence so as to reject the null hypothesis. So the prosecutor will collect evidence and try to reject, to help in rejecting this particular statement and prove that the guy is actually not innocent. Okay. So in this context, we'll be having innocent as our null hypothesis. The word innocent is in quotes. Huh? So we assume that the guy is innocent. These are like our H naught. So this claim is either true or false for every suspect. So for every suspect who is arraigned before the court of law, then this statement is either true or false for them. They are either actually innocent or they are actually guilty, so to say. Then from the evidence that the prosecutors will present before the court of law, this statement will either be rejected or it will be accepted. We'll fail to reject it. Huh? Then, or it may be false. The statement might actually be false. You find that the guy is actually not innocent, but from the evidence that we have or that we lack, you end up rejecting that statement or you accept that statement. So you notice that in the first scenario, the guy is actually innocent, but you reject that statement. So this will result to type 1 error. So then in the second scenario, the guy is innocent, it is true that the guy is innocent, and you accept this statement that he is innocent, then this will just be an okay decision. Then in the third scenario, you find that the guy is actually not innocent. The guy is actually not innocent, but from the evidence that we receive, we reject this statement. We reject this statement here. If we reject this statement and the guy is actually not innocent, this will be an okay decision. And finally, you find that the guy is actually not innocent. He's actually not innocent, but you end up accepting this statement. You end up accepting this statement. You claim that the guy, or you conclude that the guy is innocent. This will be, again, another error, type 2 error. I don't know from your own assessment, when you look at type 1 error in this context of courts or corridors of justice, when you look at these two errors, which one sounds more serious than the other? Which of the two errors sounds more serious than the other? So in this context, the first error, or type 1 error, is equivalent to jailing an innocent person. You jail an innocent person. In the second scenario is you mistakenly set the criminal free. By mistake, you set the criminal free. You let him or her go scot-free. So you notice that theoretically, or it has been proved, or it can be shown that type 1 error is the more serious of the two errors, is more serious than type 2 error. So we say that it is known that type 1 error is more serious than type 2 error. It is known that type 1 error is more serious than type 2 error. Then it is also known that the two errors have an inverse relationship. That is, as one error decreases, the other error increases, and vice versa. Okay, and then we note that the objective in hypothesis testing is to minimize both errors. In other words, maximize the probability of making the correct decisions, or the correct decision. Okay. Then still another note, we note that a type 1 error is usually determined by the researcher. So that's a good thing. We're saying that type 1 error is the more serious of the two errors, but the good news is that it is under the control of the researcher. Okay, but the problem is that the researcher may want to make type 1 error as small as possible because you have said it's the more serious of the two errors. But the problem is that as you make type 1 error very small, then type 2 error will be growing. Okay, will be growing. So let's mention that the probability of making type 1 error, is called the level of significance. And is denoted by So we use the symbol alpha to denote it. We're saying that the probability of type 1 error is equal to alpha. This is what we are calling level of significance. We're saying that this level of significance is determined by the researcher. The most widely used levels of significance are 5%, which is same as 0.05. So that's the probability that is you can set of making type 1 error. Okay, so that is making the wrong decision, 5 out of, let's say, in 5 out of 100 decisions. So out of 100 decisions that you make, 5 of them to be falling under this category. So this is the default level of significance. This is the default level of significance. So if you are solving a problem and you have not been given the level of significance, you are supposed to use 5%. You're supposed to use 5%. So other levels of significance are 10% and 1%. So those three are the most widely used levels of significance. Okay. Then we note that the probability of making type 2 error, is denoted by beta and is used to calculate something called the power of a test. It is used to obtain something called the power of a test. Okay. So that is the probability of making type 2 error is given by, or is denoted by beta. And the power of a test is defined as, is given by 1 minus beta. Okay. So this is the probability of rejecting the null hypothesis, when it is actually false. The probability of rejecting the null hypothesis when it is actually false. That is similar to saying the probability of making the correct decision. Remember, decision making revolves around the null hypothesis. So we've said that the objective of hypothesis testing is to minimize the 2 errors. So when you minimize the 2 errors, for instance, when beta is very small, when the value of beta is very small, it means that the power of the test will be very high, and that's a good thing. So we need to increase the probability of making the correct decision. So beta must be very small. But remember, we've said that as you make beta small, the value of alpha will be increasing or will be going up. And we had mentioned that type 1 error is more serious than type 2 error. So we need to strike a balance between the level of significance, the probability of type 1 error and the probability of type 2 error. You need to strike a balance. You can't set any of them to 0. If you set B to 0, your power will be at maximum. Your power will be 100%. The power of your test will be 100%. But the problem is that the probability of rejecting a null hypothesis when it is true will be at its highest also. So you need to strike a balance. You can't set any of the errors to 0. You need to strike a balance. And I've mentioned that the most widely used levels of significance is 5%, 10%, and 1%. Okay. Any question there? Any question? So we have said that the first thing is you define the hypothesis. And then we continue by saying that after formulating the hypothesis, you decide on the level of significance. You decide on the level of significance. That is alpha. And we have mentioned that you can use 5% or any other percent. For example, you can use alpha is 5%, alpha is 10%, or alpha is 1%. You can choose any of those or any other value that is given or you're required to use. Then after this, you divide. After this, you divide. So after this, you divide the possible values. The possible values of the sample descriptive measure into two sets. You divide the possible values of the sample descriptive measure, something like a sample descriptive measure, something like X bar. As we saw, there are different possible values of X bar if you are to choose all the possible samples. So you divide all those different possible values into two sets or regions. Okay, as follows. You can say if alpha is 5%, you put 5%. You put 5% of the values in the critical region, also known as the rejection region. In the rejection region, and the remaining 95%, in what we call in the acceptance region. So after you choose the level of significance, you divide the values, all the possible values of the sample measure into two sets, where one set will be called the critical or the rejection region, and the other one will be called the acceptance region. Okay, so we can illustrate. Let's recall the example that we did earlier on, where we had X bar taking the values 2.5 and 3.0. And we said that the distribution of X bar is actually normal like that. So we're saying that from this distribution, you divide the possible values of X bar into two sets. into two sets. So you can, for instance, put that as the border point, and then you say that this is 5%. You put 5% of all the possible values of X bar on one set, which we shall be calling, the shaded part is called the rejection region. And then the remaining 95% are called, or is called, the acceptance region. Okay, so you divide the entire distribution of all the possible values of the sample measure into two sets, where one side is called the acceptance region and the other one is called the rejection region. This border point here, or this line that separates the acceptance region and the rejection region, is called the critical value. The critical value. In most of the cases, the critical value will be read from either the normal tables or the t distribution tables or any other distribution or tables, even the chi-square and so on and so forth. So this value will always be read from the tables. If this was if we assume the normal distribution, and you know this is 95%, you know, on the lower side we have 95% like this. So if you know this is 5%, for instance, you will know that this is 45%. So it is easy for you to find, this is the same as 0.4500. So it's easy for you to find this value here. You should be calling Z critical. So the border point, or the starting point of the acceptance region, is called the critical value, either Z or T or any other statistic. So that's the second thing. You divide the distribution into acceptance and the rejection region. Then after you do that, then we calculate, or then you calculate the value, you calculate the value of the observation, you calculate the value of the measure, sorry, you calculate the value of the measure from the chosen sample, and say whether it falls in the acceptance region. You say whether the calculated measure falls in the acceptance region or in the rejection region. So after you set up your acceptance and the critical region like this, you don't need to pick a random sample from the population of interest. Then you compute X bar. For instance, these ones are values of X bar. You calculate X bar from that sample, and then you locate it along this line. You locate the value of X bar along that line. It will either be in the unshaded part or in the shaded part. So that means it will either be in the rejection region or in the acceptance region. If the value of X bar that you've calculated falls in the acceptance region, you accept, in quotes, you accept the null hypothesis. If it falls in the rejection region, you reject the null hypothesis. Okay, but to make our work easier, we'll not be working with the calculated value of X bar when we're testing a hypothesis about the mean. We'll be working with the standardized value of the observed sample measure. So instead of using this diagram here, we'll be using this diagram down here. So instead of using X bar, we'll be using values of Z. So for every X, for the value of X bar that you have obtained, we'll get a value of Z that corresponds to that. Then we locate it here. We locate it along the X axis here, or the Z axis here. Then we say whether it falls in the shaded part, that is the rejection region, that one, or it falls in the acceptance. So this is acceptance region, and this is the rejection region. So that tells us what to do with the null hypothesis. Then once you reject or fail to reject the null hypothesis, it is at that point when you make your conclusion about the problem at hand. You make your conclusion, and the conclusion will always be made in the language of the problem. So the conclusion will always be attempting to answer a very specific question that was being solved. Okay, so that is the introduction on hypothesis testing. I want us to go to specifically to hypothesis testing for one population mean. Hypothesis testing for one population mean, unless there's a question. Okay, so hypothesis testing for one population mean, and we shall start by looking at the steps that are involved in hypothesis testing. So the steps will be customized for one population mean, but that they can be adjusted. They can be adjusted to become the steps of hypothesis testing for one population proportion, for the difference of means, and for the difference of proportions by adjusting the sample measures appropriately and things like the standard errors. So the first step in hypothesis testing is to define or to state the null hypothesis. You state the null hypothesis, H naught. So when we are testing a hypothesis for one population mean, you define the null hypothesis as this H naught such that mu is equal to mu naught, where mu naught is the hypothetical. This value is never calculated, is the hypothetical population mean. This is a value that is being tested. This is the value being tested. The hypothetical value is the value being tested. Okay. For instance, I can make an hypothesis claiming that the mean age of students in this class is 21 years. So if I want to test that hypothesis, I'll say H naught that the mean age of students in this class, mu, is equal to 21. So here, mu naught is 21. That's the value that I need to test. That's the value that I need to test. So it means that later on, I need to pick a sample from the said class. Then I find the value of X bar. Then I test to see if that value of X bar and the hypothetical value are actually different in any significant way. Okay, so that's step number one. Then step number two, you decide. So here we're not saying you state, you decide. Decide on the alternative hypothesis. H1. And we mentioned that the decision here depends on, so this depends on the wording of the problem. The decision on the alternative hypothesis depends on the wording of the problem. It depends on the wording of the problem. And the wording of the problem might suggest one of three possible meanings. So the wording of the problem may suggest one of three possible meanings. So there are three possible meanings in every given statement of a problem. So Roman number one possible meaning is that the sample comes, if you want to test whether the sample comes from a population whose mean is not equal to. So this is one possible meaning. The sample comes from a population whose mean is not equal to mu naught. Okay. So we say that here we define the alternative hypothesis. We define the alternative hypothesis as, so this is how we define the alternative hypothesis. We say that H1 is such that mu is not equal to mu naught, meaning that mu is different from mu naught. Can either be greater, can either be less. But whether it is greater or less is not important here. We test whether it is just different from mu naught. Then you continue by saying that for this alternative, let me say this. For instance, in my earlier example, I can say that H1, that mu is different from 21. Mu is different from 21. Then you continue by saying that for this alternative, or for this alternative hypothesis, you divide, for this alternative hypothesis, you divide the critical region, into two equal parts. Into two equal parts, and put one in each tail, and put one in each tail of the distribution. In each tail of the distribution, as shown below. Before I show you, I say that this results to what is called a two-tailed test. It results to a two-tailed test. Okay, so we can illustrate here using the normal distribution. So we're saying that in this case, this is how you define your critical region if your alternative hypothesis is like shown above there. So if that's the normal distribution, okay, you put the critical region on both tails like that. You divide the critical region into two, and you put 1/2 on each tail. So this is alpha over 2, and this is alpha over 2. So in here, we have the acceptance region, which is same as 1 minus alpha. And then here we have the rejection region, also called the critical region. This one. Then, as mentioned earlier, we have the critical values. So this one, and this one. Let's call this Z1 and this is Z2. So Z1 and Z2 are the critical values. Okay, so actually I should just say this is Z1. This is Z1, but this is minus. So Z1, so then I say here plus and minus Z1. I say here plus minus Z1 are the critical values. So these values are usually obtained from the tables. If you're using standard normal distribution, you use the standard normal tables to obtain those values using the given percentages there. So that's one possible meaning of the alternative or interpretation of the wording of the problem. The number two, the second possible meaning is that the sample comes from a population whose mean is greater than mu naught, whose mean is greater than mu naught. We say that here we define the alternative hypothesis as H1 such that mu is bigger than mu naught. For instance, in our earlier example illustration, we can talk about H1 such that mu is bigger than 21. And we say that for this distribution, for this alternative hypothesis, for this alternative hypothesis, we put the entire critical region, we put the entire critical region, in the right hand, or the upper tail of the distribution, resulting what is called an upper tail test, as shown below. So we have something like this. So you put the entire critical region on one side like that. So this is your critical value. So let's just call this one Z. And this is your alpha. And this is 1 minus alpha. This is acceptance region. And then this one is your rejection region, also known as critical region. Huh? And this point here is your critical value. So this is what you call an upper tail test. Okay. Then the third possible meaning is that the sample comes from a population. Whose mean is less than mu naught, where the alternative hypothesis is defined as H1 mu is less than mu naught. For instance, we can have H1 such that mu is less than 21. And you say for this kind of alternative hypothesis, we put the entire critical region. In the left hand, or the lower tail of the distribution, resulting to a lower tail test. As shown below. So if you have that kind of alternative hypothesis, then this is how you set up your critical region. So you have this. This is the entire alpha. This is 1 minus alpha. This is your acceptance region. And this is your rejection region. And this point here is your critical value. So those are the three possible meanings. Huh? So when defining the alternative hypothesis, or when defining the hypothesis, it is very good for you to note the wording of the problem. because if you set up the wrong alternative hypothesis, chances are very high that you will end up with the wrong conclusion. You will end up with the wrong conclusion. So that step number 2 is quite important. It's quite important. Okay, so let's move on to step number 3 of hypothesis testing. Step number 1 was null hypothesis. Step number 2 was alternative hypothesis. Step number 3, you choose the level of significance. Choose the level of significance. And hence set up the critical region. Hence set up the critical region. So for you to set up the critical region, you need to use the level of significance to obtain the critical value of Z. And as I mentioned earlier, the most widely used levels of significance are 5%, 10%, and 1%. And by default, if you're not given, or if you're solving a given problem and the level of significance is not mentioned, you should, in that case, use 5%. It's the default level of significance. So let's see the possible values or the possible critical values of Z if you use the different values of alpha or levels of significance for the upper tail test, for the lower tail test, and the two tail test. So let's summarize that. Critical values of Z. So let's have a table here summarizing critical values of Z for different values of alpha and also different types of tests, either the upper tail, lower tail, or the two tail test. So we'll create a table here. Okay, so using tables, we obtain those critical values. Already we said this is plus minus 1.96. Then finally, a two-tail test at alpha is 1%. That means you have the lower tail here, you have the upper tail here. So this will be alpha over 2. For two-tail test, on each tail you put alpha over 2. So this is 0.5%. And this is alpha over 2, which is 0.5%. We're looking for this value of Z here. This is the center. Then we know that the area from the center to the value Z above, this is 49.5%, which is same as 0.4950. So we look for the value of Z corresponding to this area above the center. So 0.4950, 0.4950, 4950. What's the nearest value here? We have, this is, so the value must be here, 49.4949 and 0.4951. So this point is 1 unit less. This one is 1 unit above. And as we've done in the other examples, we pick the one that is above, or the one that is nearest, sorry. So if they're equally likely, we pick the one that is above, if they're equally likely. Then, so this is 2.58. So this is 2.58. And using symmetry, we say this is minus 2.58. So you'll come here and say plus minus 2.58. And I want you to try this at home. Find the critical values of Z when alpha is 0.1%. So this one is your exercise. Exercise, this one. So you try those ones. Okay. So that is step number 3. You choose the level of significance and then you set up your critical region. Any question so far? And step number 4, so let's move to step number 4. We say that calculate the sample mean and the sample standard deviation. In an exam setting, these values may be given, but in reality, you find that you may have to calculate them. So even in cases where they are not given, then it should be easy for you to obtain them. Okay, and then calculate the standard error of the mean. The most important thing here is you obtain standard error of the mean. Okay? Because if x bar is given, that is this is x bar and this is s. If they are given, you just need to go straight to computing standard error. And this is how you obtain standard error of the mean. So you say that if sigma is known, you obtain the standard error of the mean as sigma over root n, where sigma is the population standard deviation and n is the size of the sample. Okay. Then if sigma is not known, we estimate it, or you estimate it using S, where S is the sample standard deviation. And you say that standard error of x bar is equal to S over root n. So this will be an approximate value. It will be an approximate value because S is an estimate of sigma. Okay. So basically that's step number 4. Then step number 5, you calculate standardized value. You calculate the standardized value of x bar. And this standardized value of x bar is what we call the z. You calculate. So now we are switching from using x bar to know whether the sample falls or the sample information falls in the acceptance region or in the rejection region we switch from x bar to z. So now we'll be checking whether z falls in the acceptance region or in the rejection region. Okay. So we say that if sigma is known, so again, if sigma is known, this is how we obtain z. Z is given by x bar minus mu naught. Mu naught is a hypothetical value divided by sigma over root n. Okay, that's a familiar formula. Then if sigma is not known, we estimate it, that is sigma, using S and obtain Z as follows. And there are two scenarios. There are two scenarios. Roman 1, if n is large, if the sample is large, you continue using Z. So you say that Z is given by x bar minus mu naught over S over root n. For large n, this is for large n, and S is defined as summation of x minus x bar squared over n. When n is large, that is how you estimate. That's how you estimate the standard deviation. Then Roman number 2, if n is small, and the population is normally distributed. So there are two conditions here, or there are two assumptions here. If n is small, and the population is normally distributed, we replace Z with T. We replace Z with T in the formula there. So we have T is equal to x bar minus mu naught over S over root n. This is for small n. where population is normal, and S in this case is given by an adjusted formula. So we have summation of x minus x bar squared divided by n minus 1. So we adjust the formula of obtaining S as shown there. Okay. So where T has a T distribution, where T has a T distribution, where T distribution is that this is a probability distribution with degrees of freedom equals to n minus 1, with degrees of freedom equals to n minus 1. So this statistic here, whether Z or T, so the standardized value here is called the calculated statistic. So the value of Z obtained here, should be value of Z or T, yeah? Obtained here is called the calculated statistic. Is called the calculated statistic. That is, you can call it Z calculated in short, or T calculated. So this is the value. The calculated statistic is what we shall be comparing with the critical value. The calculated value or the calculated statistic is what we shall be comparing with the critical value. And the critical value is what you obtain up there from the tables. So that's step number 5. Then finally, step number 6 in hypothesis testing, this is when you make your decision now. Step number 6, you say whether calculated value falls in the acceptance region, or rejection region. You say whether the calculated value falls in the acceptance or the rejection region. Then make a conclusion. Depending on whether, so if the calculated value falls in the acceptance region, you accept the null hypothesis. You fail to reject the null hypothesis. But if it falls in the rejection region, you reject the null hypothesis. Then we make a conclusion. You make a conclusion or decision. And this decision here is just answering the question that was posed at the beginning. So you answer the question. At this point, you answer the question. For instance, in my case, I would answer the question, or I would maybe I would reject the null hypothesis that the mean age of students in this class is 21. So I would reject this statement. If I reject that statement, then I will claim that either the mean is less than 21, depending on my alternative hypothesis, or is greater than 21, depending on the alternative hypothesis, or I would claim that the mean is just different from 21. The mean age of students in the said class is different from 21. So basically, those are the steps of hypothesis testing. And these are the same steps we shall follow when we are testing hypotheses about the proportion, the difference of means, the difference of proportions. So at this point, I want us to have an example so that we can practice the steps and see how we can make a decision using hypothesis testing. So example 1. So we are told that the average IQ of a sample of 50 university students was found to be 105. Then you're asked to carry out a statistical test to determine whether the average IQ of university students is greater than 100 if you assume that IQs are normally distributed. Then additionally, you're told that it is known from previous studies that the standard deviation of IQs among students is approximately 20. Okay, so that's the question that we have here. So we can start by saying solution. So from the first line, we know that we are told the word average here is the same as the word mean. Huh? So the mean the mean IQ of a sample. So we are given sample values, a sample of size 50. So we know that n is 50. So the mean IQ of a sample of 50 university students was found to be 105. So this is mean from the sample. So that is X bar is a 105. Then we are told further that you are told to carry out a test to determine whether the mean IQ of university students is greater than 100. So this is the value that we are testing. This is the value that we are testing. So this is a hypothetical mean of the population. So that's the value of mu naught is 100. That's the value that we are testing, the hypothetical value. And then you are told that it is known from previous studies that the standard deviation of IQs among university students is 20. So sigma there is 20. So with this information now, and you notice that we are not told the level of significance. So if you're not told the level of significance, you assume or you let's say you let alpha be 5%. So when alpha is not given, you use 5%. So let's solve the problem. Step number 1, define the null hypothesis. So you start by saying H naught that mu is equal to mu naught, where your mu naught is 100. Then the second step, H1, is that mu will also be testing 100. So please notice that when you are defining your hypothesis, you never put anything that is coming from the sample. You only put the value being tested or the hypothetical value. So what to write in H1 or in the alternative hypothesis depends on the wording of the problem. So we need to go back to the question and check what are we asked to test? What are we testing in this question? You are told to test, perform a statistical test to determine whether the average IQ of university students is greater than 100. So we are testing this, whether mu is greater than 100. So here we're going to put a greater than sign. And once you do that, you say that this calls for an upper tail test. So you notice that the kind of test that you're going to perform, whether lower, upper, or two-tail test, depends on the problem at hand. Depends on the problem at hand. So this calls for an upper tail test at alpha is 5%. Because we're assuming normality here, so we can set up our critical region. So we're already in step number 3 here. So we need to set up our critical region like that. So in this case, we're going to put alpha or the critical region on the upper tail. So alpha is 5%. So the shaded part is your critical region. So this is your Z critical. And we observed that if you're using 5% and upper tail test, this will be 1.65. This will be 1.65. So that's your critical region. So this is your acceptance region. And this is your rejection region. So that's step number 3. Yeah? You state alpha, and then you set up your critical region like that. Then step number 4, you obtain the standardized value of X bar, sorry. So this will be given by Z, which we shall be calling Z calc to differentiate it from this other one. So there are two Z's, Z crit and Z calc. So this will be given by X bar minus mu naught divided by the standard error, which is given by sigma over root n. And in this case, we have X bar is 105 minus mu naught is 100. Then sigma is 20 divided by square root of 50. So the calculated statistic here is 1.7, let's say 68. So that's a calculated value. So now we move to step number 5. So we need to check whether this value falls in the acceptance region or in the rejection region. So we need to locate this value in the above distribution. So 1.76 will be somewhere here. 1.7, let's say 1.768 is somewhere there. It is somewhere in the rejection region. So we notice that, or we say that zcalc, which is 1.768, falls in the rejection region. Once you say that, that tells you what to do with the null hypothesis. That tells you what to do with the null hypothesis. And this is what you will do with the null hypothesis. You reject it. So hence, we reject the null hypothesis H naught that mu is equal to 100 in favor. We reject H naught that mu is equal to 100 in favor of the alternative hypothesis H1 that mu is greater than 100 at the 5% level of significance, at the 5% level of significance. So you have to mention the level of significance, because possibly if you change the level of significance, the decision might change. The decision might change. Then finally, we say that it is therefore reasonable. It is therefore reasonable. In other words, there is evidence to support. It is therefore reasonable to conclude that the mean or the average IQ of university students, is greater than 100. So there is evidence to support the claim that the average IQ of university students is greater than 100. So basically, that's how you test hypothesis for one sample mean. So any question? So before you go to example 2, you try these exercises. So repeat the above example using alpha is 10% and alpha is 1%. That's the first exercise. In the second exercise, you test at the 5% level. You test at the 5% level of significance if the average IQ of university students is greater than 103 or 103 based on example 1 above. So based on the above information from example 1, you test whether the average IQ of university students is greater than 103. Then example number 2 is here. Example number 2 is here. The annual rainfall in centimeters at a certain weather station over the last 10 years has been as follows. So the data is given there. Then scientists at the weather station wish to test whether the average annual rainfall has increased from its former long-term value of 22 centimeters. Test this hypothesis at the 5% level of significance, stating any assumptions that you make. So let's solve this example. So solution. You notice that this example is slightly different from the first example. Number one, you notice that we're given the raw data. So we need to compute the summary values from the data given. So we need to obtain the value of X bar and also the value of S. You also notice that the size of sample here is very small. The size of sample here, or N, is 10, which is a small sample. So that means we need to make some additional assumptions, and that's why we have this question here. We need to make some assumptions about the population so as to use a T distribution. Because clearly we can't use a Z distribution here. Okay. So solution, we notice that we notice that n is equal to 10, which is a small sample. Small sample. So as to use the normal distribution, we can assume that the sample comes from a normal distribution. Assume that the sample comes from a normal distribution. Okay, so that is what will help us to use a t distribution. Then we notice that sigma is not known. Sigma is not known. Hence, we estimate it using the sample standard deviation. And using the your scientific calculator, you can obtain the values of x bar and s very quickly. So x bar, we know this is given by you sum the values divided by n, and s in this case will be given by summation of x minus x bar squared over n minus 1 x square root. This is the same as summation of x squared minus n x bar, where this is squared, divided by n minus 1 square root. So I'll quickly use my calculator to obtain those values. So number 4 here. Then I start with x bar, which is 25.87. And then the value of s, number 4, equals 4.75115 something. So those are the sample descriptive measures, x bar and s. Then we can now start the process of testing hypothesis. So H naught will be what? Now, I think there's something that we've forgotten. In this example, we are given this value here. We are told that scientists at the weather station wish to test whether the average annual rainfall has increased from its former long-term value of 22 centimeters. So this is a test value. So this is our value of mu naught. That's our value of mu naught. That's our value of mu naught. So we can write it here. So we can write it there here that mu naught is 22. So that will help us in defining our hypothesis. So H naught will be that mu is equal to mu naught. Then we test that one against H1, that mu. We are testing whether the value, the mean annual rainfall has increased from its former value of 22. So we are looking whether, or we're testing whether mu is actually bigger than 22. Okay, so this calls for an upper tail. So with the above assumption, we say that this calls for an upper tail t-test. This calls for an upper tail t-test at degrees of freedom equals to n minus 1, which is 9, and alpha is 5%, because we are taught to use alpha is 5%. So the t distribution will be fully defined, or the t value will be fully defined when we know the degrees of freedom and also the value of alpha. Okay, so this is degrees of freedom. There's a problem here. Degrees of freedom is equal to n minus 1, which is 9. Okay, so let's set up our critical region using the t distribution here. So we shall have something like that. This is an upper tail test. So we shall have the entire critical region here. So this will be alpha is 5% at degrees of freedom is equal to 9. So we need to get this t crit, and we shall obtain that from the t distribution tables. We shall obtain that from the t distribution tables. So here are the t tables. In our case, we are working with 9 degrees of freedom. So the number we're looking for must be within that row. The number we're looking for is somewhere there. Then on the upper tail, we have 5%. So we're saying that this is, if we set this to be 5%, so we look for the corresponding column, which is here. This is alpha is 5%. So the critical value of T is here, 1.833 something. So this is 1.833. So this is 1.833. You can just stop there. So that's your critical value. And once you get your critical value, so that means that this is your acceptance region. And then this is your rejection region. Rejection region. Then now the next thing is to obtain a T calc, which is given by x bar minus mu naught over s out of root n, where x bar in our case is 25.87, 25.87 minus our mu naught is 22 divided by 4.7511, 4.7511 divided by square root of 10. So when you simplify that, you will get 2.576. Okay. So the next thing is to say whether this calculated value falls in the acceptance region or in the rejection region. So if you try to locate this value here on the distribution here, this will be here, 2.576. 2.576. So this means that, so we observe that T calc, which is 2.576, falls in the rejection region or the critical region. Falls in the rejection region. Hence, so that tells you what to do with the null hypothesis. You do this. Hence, we reject H naught that mu is equal to 22 in favor of H1 that mu has increased to 22 at 5% level of significance. At 5% level of significance. So we conclude that, so it is reasonable to conclude, in other words, there is evidence to conclude that the average annual rainfall, the average annual rainfall has increased from its former long-term value of 22 centimeters. So there is evidence that the average or the mean annual rainfall has increased from its former long-term value of 22 centimeters. Okay, so that is the end of that question. And before we conclude the class, I want you to try this at home. So this will come as an exercise. So exercise, you repeat the above example, that is example number 2, using alpha is 1% and alpha is 10%. You repeat that example using those two values of alpha. Okay, so that marks the end of today's class, unless there is a question.